Hi, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all very much for joining today. Our seminar is generously sponsored by 2 Sigma. It's my real pleasure to introduce our distinguished speaker today, Professor Adrian Lewis from Cornell University. Professor Lewis received his BA, MA, and PhD degrees from Cambridge University, UK. He joined Cornell in 2004 as a professor in the School of Operations Research and Information Engineering, where he completed a 3-year term as director in 2013. He has made many tremendous contributions in non-smooth optimization and variational analysis. For example, his book, Convex Analysis and Nonlinear Optimization, is a classic in this field. He has also authored nearly 100 publications, and he is a co-editor of mathematical programming. He is also a SIAM Fellow and has received many prestigious awards such as the Eisenstein Prize, the Lagrange Prize, and the Outstanding Paper Prize from SIAM, and the Informs Computing Prize. In addition, he was an invited speaker at the 2014 International Congress of Mathematicians in Seoul. Today, Professor Lewis is going to talk about smoothness in non-smooth optimization. Please join me in welcoming him.
Great. Thank you very, very much. I hope you can hear me okay. Can somebody just give me yeah, you can hear me fine, great. So yeah, I wanted to thank the organizers in particular. I mean, this is a really imaginative enterprise, and it's extremely timely, and I commend you for putting it together, and I commend your energy too, because putting these things together takes a huge amount of energy. And I want to thank all of you out there. I can't see you for the most part, but I know that you're out there, and I wanted to thank you for choosing to spend a beautiful sunny afternoon, at least in Ithaca, listening to me shamelessly promote some of my own research ideas. So thank you very much. I'm going to try to make it fun, and then I think the way it works is there'll be questions at the end. Normally, I love people to interrupt, but I'm going to talk to a vacuum and then see who's got questions at the end. So bear with me. Okay, so the theme of this talk is very much one of the driving themes of my research, especially currently, which is the interplay between smooth and non-smooth ideas in optimization and in more broader variational problems. So how do those two ideas interplay? So lots of optimization problems are not smooth, but that non-smoothness doesn't just come in some arbitrary kind of nasty way. It's often got some either very explicit or implicit structure that one can try to capitalize on, and that's what this talk is going to be about. So it's about trying to capitalize on smooth ideas using a Newtonian kind of philosophy. And so without more ado, I'm going to jump in. Let me start again, actually, just by thanking lots of my co-authors, students, ex-students. Much of the work that I'm going to talk about here is really not my work, but theirs. And so I'm lucky to work with a lot of very smart people. So thanks to them too. Okay, so let me start by posing 3 questions. So the first question that I kind of just posed already, which is why is it very often the case that we see smooth kind of behavior in apparently non-smooth situations, non-smooth optimization, generalized equations? Where does this smoothness come from? So second question, if we know it's there, can we capitalize on it somehow? Can we use Newtonian kind of ideas to capitalize on that kind of smoothness? So for example, just to take an example, if you think about projection onto a set, even a convex set, then that convex set might not be smooth, but it might be just a polytope, something like that. Very often, though, when you make small perturbations to the point that you're projecting, the behavior of the projection is smooth. That's a sort of a generic property, in fact. So can we capitalize on that somehow? So for example, in the projected gradient method, so if we think about minimizing a smooth function f over a closed set Q, maybe convex, So we can translate that into its optimality conditions using the normal cone operator. And then in that kind of light, we can think about projected gradient methods. So there's the basic projected gradient method where we keep taking a step in the negative gradient direction, scaled somehow, and then project the answer back onto Q, and we keep updating. So when we do that, because of this smooth kind of substructure sitting inside Q that we often find, that projected gradient algorithm automatically kind of identifies smooth structure inside Q. So in other words, after finitely many iterations, it lands on some manifold, some smooth surface, and then after that, it behaves. All the convergence analysis really reduces to that manifold. So this question really comes down to can we capitalize on that in a Newtonian kind of way? Can we accelerate using Newtonian ideas? All right, third question. So these kind of ideas really depend heavily on sort of explicit structure or some kind of structure that we can get a handle on. But what if we don't have any explicit structure at our disposal? What about black box kind of algorithms? So what about using just an oracle? Can we hope to do things quickly? Can we hope to get good, maybe superlinear local convergence for just a black box algorithm for non-smooth optimization? So that's been kind of like a holy grail in non-smooth, even convex optimization for a long time. And I'm going to try to make a case to you that there is promise in that direction. And let me just show you one picture that hopefully will demonstrate that. So this is a picture of an eigenvalue optimization problem. So it's plotting black box evaluations against the gap, the optimality gap, if you like, how far you are away from optimality. And I plotted a couple of methods here. Maybe I can just shift these down so I can see a little better. On this green line is BFGS. That's a sort of a favorite heuristic of mine. You just apply the BFGS method to this non-smooth problem. The blue line is a rudimentary bundle method. And this red line is a sort of an acceleration technique that I'm going to talk about later. And so this is a moderately sized problem, at least in the standards of non-smooth optimization. So it's got about 50 variables, and it's an eigenvalue optimization for 25 by 25 matrices. And you can see that it's running about after about 700 iterations, that acceleration scheme has reached machine precision. So it's extremely accurate. You kind of see this very fast convergence after a certain point when you initiate it. So I'll talk about this algorithm, but basically it's there as a teaser. I want to kind of tease you to sort of suggest that the answer to this question 3 may be yes, that there's more promise to that than we might have imagined in the past. Okay, so that's where I'm going. All right, so let me start with question 1. So where does this smoothness come from? And I'm going to start with a somewhat non-standard example because it's something that I've been thinking about recently. So let's see. So the example I want to think about is the numerical radius of a square matrix. So this is a very simple convex function. So you take so these matrices are not symmetric. They're just n by n complex matrices. They might be associated with some dynamical system. And the numerical radius looks at what we sometimes call the field of values or the numerical range, which is the set of values in the complex plane that you can get by forming U star AU for a unit vector U, so a unit n vector. So you look at all those complex numbers you get, that turns out to be a compact convex set. You look at how far away from 0 it can get, and that's what you call the numerical radius. So that quantity, it turns out actually to be a norm, although not a matrix norm in the usual sense, because it doesn't have the multiplicative property. But it's a very nicely behaved convex function, and it's sort of a rather rudimentary way of bounding transient dynamics in dynamical systems by virtue of the famous power inequality. So what is this saying? So you can bound the norm, the 2 norm of a matrix by twice its numerical radius. That's an easy thing to check, And the numerical radius itself satisfies this so-called power inequality, this second inequality here. So using this single number, the numerical radius of the matrix, and thinking about how it changes as you raise it to certain powers, you're bounding the size of the iterates of this dynamical system. So it gives you this sort of rudimentary control. So one thing that you might want to do in a sort of a rudimentary systems analysis is to try to make the numerical radius of a matrix small if it's got some parameters in it. And if you do that, something rather surprising happens. So you get some rather unusual matrices, it turns out. So what do those matrices look like? So just to give you an example, what I did is I computed the proximal point of lots of random matrices. So basically, I took a random matrix Y, n by n matrix Y, and then I computed the proximal point, with some appropriate scaling lambda. So I minimize rho of A, so minimize over A, rho of A plus the norm squared. So that's the proximal operator. And so that's kind of, if you like, a surrogate for a typical optimization problem involving a numerical radius. And it turns out that when you do that, that very often the matrices that come out are rather unusual in the following sense, that if you look at their field of values, so these vectors, these points in the complex plane that you get exactly a disk, so a disk centered at 0. So you get a perfect circular disk. So somehow the optimization of computing the proximal point generates these so-called disk matrices whose field of values are a disk. Okay, so let me illustrate that numerically. So what I did is so what we computed is so we generated 1,000 random matrices Y, computed this proximal point, the proximal matrix 1,000 times, and then measured somehow or other whether the field of values was a disk. And there are various ways you can sort of track that. So I've written 4 of them here. So the first one done via ChebFun, if you're familiar with the ChebFun package in MATLAB, just basically compares the inner radius of this field of values with the outer radius, the numerical radius, and tries to see how close that is to 1. So that's one quantity you can measure. You can actually check algebraically whether a field of values of a matrix is a disk. There's an algebraic, slightly complicated algebraic check for that, and you can measure that. It's actually, these matrices turn out in this experiment to be totally characterized just by being singular. So it's exactly the singular ones that you see. So you can just measure the smallest singular value. Or in fact, they also have 2 by 2 null Jordan blocks. And so you can measure the distance to that. And so what we did is we took 1,000 examples, ordered them in sort of monotonically by this measure, and then looked to see, how many of them are disks and how many of them aren't. And what you see is a kind of a phase transition happens. And so just to explain this picture a little bit, so this top column is n, the dimension of the matrix. So these are 2 by 2 matrices, 3 by 3, 4 by 4, and so on. And this is the measure, and you can sort of see that about about 2/3 of the examples of these 1,000 matrices have this measure very, very small, so around 10 to the minus 8 or smaller, whereas the remaining third have it much closer to 1. So there's kind of a clear phase transition that happens, and it doesn't matter which measure you're looking at, the phase transition is very, very, very clear. So and the same thing happens with you start to get a few more numerical problems as the size of the matrix gets bigger, but the phase transition is very clear. And so the point is this, that somehow the optimization produces these very special matrices, which in this case are matrices with field of values at disk. And that's kind of surprising because that's a small set of matrices. So you can actually measure the dimension of that set. It's got codimension 2n. So in this whole space, which has got dimension 2n squared, so real dimension 2n squared, the disk matrices have dimension 2n squared minus 2n. So it's a rather small set, and yet somehow the optimization forces you onto this small set. So the question is why, right? So why does that happen? So it's sort of a curious phenomenon. All right, so that was one slightly, non-standard example. So let me, cut to the chase and sort of say, well, what's going on here? So what is going on is this idea that I've tried to push now for a couple of decades, which is the idea of partial smoothness, which is an idea that grew out of active set philosophy in classical nonlinear programming. So the idea is that non-smooth optimization is not arbitrarily nasty. As I said, there's structure sitting there. When you look at random instances, the solution of that random instance typically is solved on some manifold of solutions where the solution depends smoothly on the perturbation that you make to the input. So, and there are lots of examples of this. So the classical example, as I said, is classical nonlinear programming, where you think about the active set, okay, the set defined by the active constraints at the point you're looking at right now. That's a smooth manifold. Semi-definite programming, same kind of phenomenon there. It becomes a question of the rank of the optimal matrix. And very often when you make a small perturbation, the rank of the optimal solution doesn't change. So the solution moves around on these manifolds of fixed rank. Very popular problem in machine learning, the lasso type of problem, high-dimensional statistical kind of approach. So we're very, we like to look at non-smooth regularizers like the L1 norm or the group lasso kind of regularizer. And again, the idea of that is to force exactly through this phenomenon to try to force some sparsity in the solution. And very often what one sees is some fixed sparsity pattern that then doesn't change under small perturbations. And then the example that I just did, which was came out of some joint work with Michael Overton and Jaiyan Han. Okay, so there's history here in this idea that goes back a long way of trying to generalize this notion of active sets in nonlinear programming. So that generalization notion goes back to work in the 80s, Jim Burke and George Murray, Steve Wright's notion of identifiable surfaces in optimization, and then much more sophisticated work by Bob Mifflin, Claudia Sagastizabal, involving VU decomposition ideas, which is sort of a parallel notion to this notion of partial smoothness. Okay, so what has that got to do with algorithms? So let me see if I can make a case to you that one would like to be aware of partly smooth kind of structure when one is thinking about algorithms. So it's easy to check that lots of first order methods, especially proximal based methods, methods using some kind of proximal operation, identify this manifold associated with partial smoothness. So by identify meaning in a finite number of iterations, you land in some smooth structure that then drives the convergence of the algorithm. So for example, this was noticed 15 odd years ago. This is one of the early papers noticing that happens with the lasso problem with L1 regularization. The proximal gradient iterates land on the correct sparsity pattern and then converge linearly after that. So what's going on geometrically is exactly this kind of picture here, where you have this non-smooth regularization term that generates this sort of characteristic structure. It kind of looks like the keel of a boat, where you have some nice smooth manifold sitting inside the graph of the function, and the optimal solution moves around on that manifold as you perturb something. Okay. So there's the classical picture. One nice example where the notation is suggestive. It's really the nuclear norm in eigenvalue optimization, and so let me move this again. So, for example, in nuclear norm regularization, if one is trying to encourage low-rank solutions of a matrix optimization problem, then the proximal gradient method, which in that setting becomes soft thresholding singular value or thresholding singular value, those iterates settle on a fixed rank manifold and then converge linearly to the solution. So again, same kind of phenomenon that was seen a decade before in L1 regularization. All right. So I want to try to make the case that the best way to understand this is not through optimization so much as through the optimality conditions that the optimization problem has. And so that sort of translates you from an optimization setting to a generalized equation setting. So, so we're going to shift attention from trying to find a minimizer to trying to solve a generalized equation that looks like the optimality conditions. Okay, so there's the optimality conditions, at least if you're familiar with the convex setting. So then, so what I want to think about then is what is this sort of smooth substructure, this partial smoothness mean for a general generalized equation? So you've got some set valued operator that describes maybe the optimality conditions or a variational inequality or something like that. You've got some variable you're trying to find. You've got the data, which in this case is 0, and you want to solve that inclusion. You want to find a u so that that solves the inclusion, or if you like to think of it that way, you want to invert this set valued operator phi. So as I said, variational inequalities gives you one example. Somehow this didn't get updated. I'm not quite sure why, but you want to find a point x in the set Q so that this variational inequality holds. So one way to translate that into a generalized equation is using the normal cone operator. And so one wants to solve this generalized equation with kind of a smooth part and this normal cone operator sitting inside of it. So that's one example. Another example, composite optimization. It's easy to break down the optimality conditions for this sort of popular setting where H is maybe a convex function, C is a smooth map from Rm into Rn, for example, Rn into Rm. And then one can decompose the optimality conditions into a way that makes it rather appealing to look at a generalized equation. Okay. So I want to try then so having taken this step back, I want to try to describe what it means for a generalized equation to be partly smooth around a particular solution. So where does this smoothness come from? So here's the definition that I think so this is some joint work with Jingwei Liang that we think sort of captures nicely the idea of partial smoothness, and it has the great merit that actually it looks much simpler than the corresponding ideas for optimization, because it reduces it to one very simple differential geometric condition. So we want to think about a set valued operator. We've got an associated generalized equation that we want to solve to find some solution for some given data. So in other words, we want to solve the inclusion that V bar belongs to phi of u and U bar is one particular solution. So what do we mean by partial smoothness? So here's the proposed definition. So the proposal is that the smoothness comes from the fact that around this pair U bar V bar in the graph is locally a manifold. So here's a very, very simple example. We've got this set valued mapping phi. There's one particular solution where 0, so V bar in this case is 0. And the graph, sure enough, around that point is a manifold, in this case just a straight line. Okay, so that's the first ingredient. So locally the graph of the thing defining the set valued mapping is a manifold. And then, and this is the key point, the projection operation that takes you from the graph, which locally is a manifold, to the domain, to the U space. That projection operation is in differential geometry language constant rank. So what does that mean? That means that literally that means that if you look at the tangent space to the graph, which is a manifold locally, the projection of that tangent space has constant dimension. Okay, so that's clearly the case here. The dimension of the projection is just 0. So an example where that doesn't hold would be something like the cube root function. So if you think about the cube root, then the tangent space projects onto the whole u-axis except at 0 when it just projects to 0, so that the projected tangent space doesn't have constant dimension, and that's what causes things to break. Okay. So then it's sort of kind of obvious, actually, that asymptotic solvers, that many asymptotic solvers are going to identify this active manifold. So what is the active manifold? The active manifold is exactly the projection of the graph around this point. So in this case, the active manifold will be literally just that point. So you take some neighborhood of the pair of points, the solution and the data point that you're interested in, look at some small neighborhood, project it onto the domain, look at that, that's what we call the active manifold, okay? And that's the thing that gets identified in many algorithms. And why is that? Well, many algorithms generate a sequence of points in the graph approaching the point of interest, and therefore automatically they're going to get projected down to something lying in M, almost by definition, essentially. So it's almost a tautology that you're going to identify that manifold. Okay. So that's the notion of partial smoothness, and then the case that I want to make is it's much easier to think about it this way in terms of the optimality conditions by thinking about this constant rank property, which is fundamentally what drives it. Okay, so what's the basic example? The basic example is to think about maybe either convex sets or more generally Prox regular sets, sets that have a locally unique projection. Think about linear optimization. So linear optimization, we're interested in minimizing this linear function, and you want to solve, so you translate this minimization problem into this generalized equation using the normal cone operator. So what does partial smoothness mean? So there's the picture, and again, it's sort of, I mean, it's more concrete and we understand it better geometrically, but as you can see, it's a fair bit more complicated to describe. So what's it saying? It's saying that the set has some kind of what you might call a ridge. It's a manifold sitting inside the set, which looks like a ridge in what sense? So it looks like a ridge in the sense that the normal cone, as you move around on this manifold, the normal cone, this yellow thing here, behaves in a continuous fashion and spans the normal space to the manifold. So that's what gives it the characteristic kind of sharpness around that creates this ridge type effect. And so you've got this smooth, non-smooth interplay. You've got smoothness sitting in this manifold and this sharpness that comes from the normal cone operator, spanning the normal space. So so in that case, when you have this structure, the normal cone operator is partly smooth in the sense that I just described in that constant rank condition. Okay, and in some sense they're very close to being equivalent, in fact. So those two properties. And so, you know, in that kind of setting, exactly what I described at the outset, if you think about the projected gradient method and you have a unique solution, then you know the projected gradient method will converge to it. And so automatically, when you do these iterates, after finitely many of these iterates, the iterates will land on this manifold M. So they identify this manifold M. So you see whatever it might be, the sparsity or the rank of the solution after finitely many iterates. Right? So that's the notion of identification. So that's one example. Second example that I want to talk about, I'm going to come back to later in the talk, which is the example now of subdifferentials of max functions. So what's a max function? So a max function is a maximum of a bunch of smooth functions, in this case k. So I've got some smooth functions, I look at their pointwise maximum, and I want to look at what happens when I minimize this max function. So I want to suppose that I've somehow solved that problem. So I've got a critical point. So we're going to call it a strictly active critical point if all of these functions are active at that point. So in other words, they all have the same value. And 0 is a subgradient, if you like, or in other words, there's some strict convex combination of the gradients at that point x bar, which is 0. Okay. And furthermore, I want to assume that this affine system, if you like, has a unique solution. So in other words, the gradients are affine independent. So as I said, this is a strict convex combination. So there's something that looks like strict complementarity here. There's something that looks like a sort of a linear independence constraint qualification here. So this is all the sort of strongest conditions that you could hope for. Okay. So under those conditions, assuming that you've got this particular kind of critical point, then the subdifferential operator, which is defined here. So this gives you exactly the subdifferential of this max function at any point that you might be interested in. It just says, okay, take the gradients of the active functions and take their convex hull. That's the subdifferential. That subdifferential operator is partly smooth relative to this active manifold where all the functions are active. So around this point x bar, you get this partial smoothness property of the subdifferential. So it's exactly what you want. Okay. So again, we'll come back to this example later. So it's a good example to internalize. So max of k functions, strictly active critical points, so affine independent gradients, all the functions are active, strict complementarity, then the subdifferential is a partly smooth operator. Okay. All right. So, of course, this wouldn't be very interesting if it wasn't a common phenomenon. And so I very quickly want to make the case that this is a common phenomenon. And it's a common phenomenon. Why? Well, for the same reason that Sard's theorem says that the Newton iteration usually works for smooth functions. So Sard's theorem says that, if you have a map from Rn to Rn that's sufficiently smooth, C2 in fact, then almost no right-hand side values are critical. So for almost no right-hand side values does the Newton method fail because the Jacobian's not invertible. So that almost never happens. That's Sard's theorem. And there's an analog of that for set-valued operators and generalized equations, at least in concrete settings. So what do I mean by concrete? So as an example, let's think about semi-algebraic equations. So a semi-algebraic operator is one with a graph which is described by a finite union of finite intersections of polynomial level sets. Okay, so we've got this kind of finite union of finite intersection of a bunch of polynomial level sets, either strict or non-strict. So I want to assume that this operator, these things are typically easy to recognize. And I want to assume that this one that we're looking at in particular has got rather small graphs. So remember, the graph sits in R2n, and I want to assume that the graph is n-dimensional, which is what happens for a smooth map, for example, or a monotone operator, or as it turns out, the subdifferential of a convex function, or more generally, non-convex functions too. So, subdifferentials, monotone operators satisfy this property. Okay, so then it turns out that there's a Sard-type result that happens. So if you think about a generalized equation with a generic data vector y, then around that data vector y, the inverse is rather simple. So it breaks down into finitely many actually analytic maps. There might be none of them because the equation might not be solvable, but there are no more than a finite number of them. And around each solution, so xi, which is gi of y, that particular solution, this partial smoothness property holds. So you get this identification property. So partial smoothness happens. So in other words, partial smoothness is a generic kind of property of generalized equations. If you're making a random choice of the right-hand side of some concrete generalized equation, then partial smoothness is going to hold. So it's kind of nice. And actually, furthermore, we can translate this generalized equation into an intersection property. Just thinking about the way the graph intersects essentially the x-axis, and that intersection is actually transversal generically too, and that's going to be useful in what we're going to do next when we think about algorithms. Okay, so thinking about algorithms, so how might we then describe an algorithm that tries to capitalize on this inherent smoothness? So we could, as I just illustrated, recast this equation as a set intersection problem. So we could think about intersecting the graph, which I'll call the set x, with what amounts to the x, let's call it the u-axis, which is just Rn cross 0. And let's suppose that intersection is transversal. Okay, so in terms of the sets, that just means the normal space to this graph, the normal cone to this graph intersects the normal space to y, which is just the v-axis, if you like, should be 0. So that's transversality. So then it's sort of easy to describe a Newtonian kind of an algorithm for solving this, and it would go as follows. So it basically says, okay, start out with a point on x sitting up here, linearize this set x. Okay, so take a linear approximation to x. So that linearization under this transversality condition is going to intersect y at a point where the error is sort of quadratically smaller than the error that you started with. So essentially by the nature of this linearization process. So that's the first step. And then you want to get yourself back onto X. So how do you get yourself back onto X? Well, you sort of somehow project yourself in some Lipschitz manner back onto the set X, and you want to do it in such a way as to fix the solution Z. Okay, so you want to somehow project yourself back in a Lipschitz way that fixes Z. Okay, so you start out on X, you linearize to get to Y, that's the Newton type idea, and then you project yourself back onto X to restart the algorithm. And so what does that become in our generalized equation model? So that the first step linearizes the generalized equation, so some kind of generalized notion of derivative. You solve it, and then you get yourself back using the partial smoothness, the sort of smooth substructure that you know is going to kick in when you get close to the solution. So you project onto the active manifold the point that you found, and then get yourself back onto X by finding maybe the smallest element of the image of the new point, and then you iterate. And what one can show is that converges quadratically, not very surprising. Okay. Okay, so that's sort of nice, but it needs a lot of structural knowledge of the subdifferential. And there are lots of examples of algorithms that use that kind of structural knowledge. So underlying this is actually the sequential quadratic programming philosophy. More generally, these ideas of semi-smooth Newton methods, lots of people have worked on those over the years, but all of them depend on some kind of structural understanding of what the subdifferential of f is, or some kind of way of breaking it apart. So what about a black box idea? Okay, so what if all you have is an oracle for linear approximations to, let's say, a convex function f at input points? You want to minimize this convex function f. What do you do then? Well, one very popular approach, probably the dominant basic approach in sort of moderate-sized optimization, are bundled methods. So there's a very nice survey in Claudia Sagastizabel's International Congress talk a couple of years ago now. And the basic idea of a bundle method is a sort of stabilized cutting plane idea, where you take a sequence of null steps that enhances the cutting plane model, and then you take a serious step to improve the solution, and then it turns out, in a more sophisticated way, you can try to accelerate that using these VU ideas that Claudia has sort of promoted, and that has the potential to accelerate these serious steps. It's a rather sophisticated construction that uses a kind of a quasi-Newton idea to try to build Newtonian approximations here. So I want to ask a simpler question, which is, well, can we do this in a simpler way using quadratic approximations instead of linear approximations? So various people have thought a little bit about this, but I want to here take a slightly different approach to the way that they've gone about it, and you'll see what I mean as we go ahead. So we're going to, again, think about a black box method. We don't know what the structure of the problem is, but we somehow want to use quadratic information instead of linear information, and try to accelerate the algorithm. All right. So how might we get that quadratic information? Well, convex functions, it turns out, are twice differentiable almost everywhere. So if you pick a random point, this convex function is going to be twice differentiable there. And in fact, lots of algorithms, if you randomize them to start with, for example, then they don't encounter this negligible set n, this measure zero set n, where the function is not twice differentiable. So BFGS, for example, that's a basic assumption that we make, that we never see a point where the function is actually not smooth, even though the optimal solution is going to be one of those points typically. Okay, so as the algorithm progresses, it doesn't hit that negligible set. And so what if this oracle, so normally an oracle would return the function value and the gradient that performs the role of the subgradient. So what if it also returns the Hessian for these points that you encounter? So the question is, can you use that to build yourself some better idea, some faster approximating scheme? So what are we aiming at with such a method? So what we're aiming at, we can't hope to find a point where the gradient is small. So what we aim instead at is to try to find a bundle, and I'm going to fix the size of the bundle at some number k. I want the diameter of this bundle to be small. So what I hope to find is a bunch of points close together where some convex combination of the gradients, some weighted average of the gradients is small. Okay, so in other words, the diameter of this bundle is small, and the optimality measure, which is how far 0 is away from the convex hull of the gradients, that is also small. So if both of those are small, then we've in some sense nearly solved our problem. All right, so what's the intuition here? Why do we want to do that? Well, the reason that we want to do that is that this convex hull of the gradients of this bundle, as the bundle shrinks to the point x, that convex hull converges to the subdifferential of f. That's the intuition. So for convex functions, or more generally actually for Lipschitz functions, we get this. We can approximate the subdifferential by convex combinations of gradients nearby. And so if we can find 0 as a convex combination of gradients, then we're approximately satisfying the optimality condition. So that's kind of what we want to do. All right. So so the method that I'm going to describe, which is some joint work with an ex-PhD student of mine, then tries to do exactly that. So it says, okay, so we're going to do the obvious thing. We're going to carry along k reference points with us, and I'll talk about k in a moment. And we're going to use the oracle to do the obvious thing, which is to build the linear approximation that you would usually use in a bundle method. But now we're also going to build the quadratic approximation too, which has got this Hessian sitting in it. Okay, so we add the second order term. So, and then what do? So we start out doing the kind of obvious thing that one would do, kind of like what one would do with a bundle method. So the obvious thing is, first of all, to try to look for a small convex combination of the gradients that you have. So that's basically sort of trying to figure out, well, how well are we doing so far? Okay, so we look for the smallest convex combination of the gradients that we can find. So we find bundle weights, so weights for each of the points in the bundle. They're non-negative, they add up to 1, and they try to minimize the norm of the corresponding weighted average of the gradients. That's a natural idea. Okay, so now the next step is the sort of key idea, which is that armed with those weights, we now form what we're going to think of actually as a kind of a Lagrangian. So now we're going to build that weighted combination of the quadratic approximations, and we're going to try to minimize it over an approximation of the active set, which we get by linearizing the linear constraints. So there's the sort of key engine of the method. So we're going to try to find a new reference point. So it's going to replace one of these old reference points by minimizing the corresponding weighted average of the quadratic approximations, subject to the constraint that all of the linear approximations are equal. Okay, so we're forcing all the linear approximations to be equal for each point in the current bundle. And over that affine space, we're minimizing this quadratic approximation, this weighted average of the quadratic approximations. So we solve that problem. That's basic linear algebra. So it's an equality constrained quadratic program. It's easy to solve. And then we take that new point that we found, and we use it to replace one of the current reference points. So which reference point do we use it to replace? Well, there's various heuristics, but one heuristic is just to choose the one with the nearest gradient. Okay, so we just pick the reference point with the gradient that's closest to the gradient of the new point that you've just found, and replace it. And then you repeat, and that's all it does. Okay, so that's the algorithm. So again, you fix the bundle size, you make what amounts to a least squares estimate of these weights to try to minimize the norm of the subgradient. You solve this quadratic subproblem, weighted average of the quadratic approximations, subject to the equality constraints, and then you replace. So that's the algorithm. All right. So where does this idea come from? Well, so what's the idea? The idea is we're going to model this non-smooth function by a max function, exactly along the lines that I just talked about before. So you're going to say, okay, f of x is approximately equal to a max of some functions that I don't know. Okay, I don't know what these smooth functions are. Okay, but these smooth functions are going to match the function the underlying function up to second order around each bundle point. So each particular bundle point, we've got some smooth function that matches the function there. And then we're going to think about modeling the function that we've got by this max function. And then what we're going to do is do a very traditional sequential quadratic programming kind of step on the corresponding optimization problem. Okay, so how would you do that? Well, you introduce a new variable, minimize t subject to being less than or equal to each of the functions in this max, and then apply sequential quadratic programming one step of that sequential quadratic programming algorithm to those to that problem. How do you go about doing that? Well, that's very traditional. You basically estimate the Lagrange multipliers by least squares. That's what the algorithm does. You minimize the quadratic approximation of the Lagrangian. That's the weighted average of the quadratic approximations. Subject to the linearized constraints, I'm going to assume that they're all active because this is going to be a sort of a local method. So I'm going to assume that all of the constraints are active. So subject to the linearized constraints. And then that new point should be much better than the model's most closely matching component, and we're going to prove that exactly that in one particular setting in just a moment. So that's the motivation of the algorithm. All right, so so here's a theorem that says that this actually works, at least if the underlying function really is a max function. So if the function that you're applying it to turns out to be a max function, you can't see what it is. The algorithm can't see what those components are. But if you apply it to a max function where each of those components is smooth, and so with one extra assumption that now you're in this strongly convex framework, so these functions all you could subtract a small multiple of the norm squared and they stay convex. And that's happening around some strongly active critical point, x bar, so exactly the assumptions that we had before, then good stuff happens, providing that you start it with a good bundle. So this is a local method. You have to start it with a good bundle. So what's a good bundle? So a good bundle is going to be what I'm going to call a full bundle. Okay, so a full bundle means that corresponding to each of these components, I've got one of the reference points where that function is largest. Okay, so providing you start with a nice bundle, size k, picking up each of the active functions, and supposing that you start sufficiently near the critical point, then actually you get quadratic convergence. Then this k-bundle Newton method converges k step quadratically to x bar. So in every k steps, the error is quadratically smaller. Okay, so again, I emphasize the algorithm doesn't need to know this structure to be implemented. But at least on functions that have this structure, it converges quadratically locally, k-step quadratically locally. So what I want you to notice is that the bundle size k, which I haven't talked about yet, and the geometry, the non-smooth geometry, the partially smooth geometry of this active manifold are closely related. So those two dimensions, k plus the dimension, need to add up to the number of variables plus 1. That's what drives it. And in the particular case, when k is 1, we're thinking about smooth problems, and this is just exactly the classical Newton method. So you've got the classical Newton scheme. All right. So let me show you a couple of very simple examples. So this is an example which is a max function. It's just a function of 2 variables. What I'm going to do, I'm going to plot the objective calls against oracle calls. So we're going to plot the number of times you call the oracle against how the objective value goes. Okay. And what I'm going to do is I'm going to compare what a rudimentary bundle method, a very untuned, naive bundle method, throws away all the cutting planes at each serious step and just restarts. How that performs, how BFGS, again, pretty untuned, behaves, and how this behaves with this actually what's going to be a two-bundle Newton method. So we're going to carry along 2 points in the bundle. Okay, so we're going to have a naive proximal bundle. The performance there, non-smooth BFGS, I hope you can see that in the light green. And then this two-bundle Newton scheme initiated at some point. And what I'm going to do is I'm going to use the naive proximal bundle scheme to initiate this Newton scheme at some point, and you'll watch it sort of accelerate away. And when I do that, I'm going to keep track of the objective, how far the objective is away from its minimum value, the optimality measure, which the optimal value is 0, by the way, fairly obviously. The optimality measure, which measures what the smallest convex combination of the gradients is, and the diameter of the bundle. Okay, so 3 algorithms, and that's what the picture looks like. So you can see that we do about 30 iterations. After about a dozen iterations or so of this naive proximal bundle method, which is this sort of brown line here. So remember, we're plotting oracle calls, and so it's doing lots of null steps, building up some information. We initiate it, and then the algorithm just takes off and hits pretty much machine precision in a few iterations. Okay, so behaves very well, exactly as you would hope, and exactly as the theorem suggests, because this is a max function. There's BFGS, which sort of goes along steadily, but again, hasn't been tuned very well. But you can see there's a sort of dramatic effect of being able to solve this problem really, really precisely. Okay, now of course that is a max function. This wouldn't be very interesting if it was only applicable to max functions. So what happens on a non-max function? So let me give you a slightly less trivial example. So this is an eigenvalue optimization problem. I'm trying to minimize the maximum eigenvalue of a 3x3 matrix with trace 2 and with first entry equal to 0. And so you can parameterize that with 4 parameters. There it is. That's not a max function, so you can't write that as a max function around its minimizer at 0. I've shifted the value for plotting purposes by -1. And I'm just going to do the same thing again. So I'm going to plot a naive proximal bundle method, the BFGS method, and this now 3-bundle Newton method. So it turns out it is partly smooth relative to a 2-dimensional manifold. You can check that analytically. So a good choice here turns out to be k equals 3. And if you do that, here's the picture that you get. And let me see if I can see that a little better myself. So you can kind of see again, this time we do about, 50 odd iterations. We start out, we initiate the now 3-bundle Newton method after about 15 odd iterations. And again, you get, so now it's not quadratic, but it's pretty fast. And again, getting down to close to machine precision in 30 odd iterations. So it's the acceleration is quite pleasing, let's say. So it's promising. So and again, I emphasize this is not a max function, so the convergence theorem doesn't apply, but the method seems promising. Seems to really accelerate what's going on. Okay. Let me see how I'm doing for time a little bit. Okay, so let me very quickly walk through the proof just to give you the idea what's going on. So again, there's the setting. So what's really driving this? So any point on the active manifold. So if you think about a point on the active manifold, these full bundles. So these bundles that pick up at least one of the active functions, so one of the active functions each. So they give you an approximation of the subdifferential on the active manifold. So these gradients, in other words, this local information is giving you correct non-smooth information on the active manifold. So that's the first piece of information you're getting. And the Hessians, although it's a little counterintuitive, you wouldn't have thought the Hessians would give you any information about a non-smooth function. They are actually correctly predicting the curvature, at least on the active manifold. So on the active manifold, it's not clear what these things mean off the active manifold, but on the active manifold, they predict the curvature. And so when you put those two ingredients together, the sort of sharp behavior of the subdifferential that comes from the subdifferential, and the smooth behavior that's coming from the Hessian prediction on the manifold, you get a Newtonian kind of error effect where the error reduces quadratically after you've done your Newton step. So then you do this replacement step, and the fact that the bundle is a full bundle means that the way that you do this replacement step keeps that full bundle property because of the assumption of strict activity, which is essentially the strict complementarity condition. And then each reference point gets updated after a number of steps, after k steps, by the strong convexity condition. So you guarantee that you update every reference point so often by strong convexity. So that's very quickly the proof. Okay, so how do you find an initial bundle? That's the million-dollar question, of course. You've got to decide on k, on the size of the bundle, and how do you find it? So the way that we do that is by relying on these more global type of algorithms to give us information about the size of the bundle and what it should look like. So whether it's a bundle method or BFGS or some kind of gradient sampling kind of approach that we also like, as they move along, they asymptotically generate approximations to the subdifferential. So the subdifferential is approximately, the optimal solution is approximately given by convex combinations of gradients in the tail of the sequence that you're generating. And so what you can do in practice is look at some set of points in the tail of the sequence, look at the gradients, numerically estimate their affine span, the dimension of their affine span, or the convex hull, whichever you prefer. So you can do that numerically by a singular value computation. So you estimate some kind of robust rank, if you like, of the coming from these gradients with ones appended, and then you pull out a maximally affine independent subset to give you your initial bundle. So you choose an initial subset of size k where those gradients are affinely independent, and that's the initial bundle that you start with. So that gives you k and the initial bundle. So that's basically the heuristic that we use. All right, now. So how effective is it? Well, I showed you that teaser at the beginning. So here's that teaser. It's an eigenvalue optimization problem. There are 50 variables. It's an eigenvalue optimization problem for 25 by 25 symmetric matrices. That's partly smooth. It's got an active manifold where the maximum eigenvalue has got multiplicity 6, as it turns out. That's a 30-dimensional manifold. So that sort of suggests the size of the bundle should be 20, I guess. And here's the behavior of the algorithm. So again, I've just concentrated on BFGS. That's the green line. The blue line is a bundle method, a proximal bundle method. And after 500 iterations or so, we say, okay, now we want a really accurate solution. So we apply this bundle Newton method with bundles. I guess that it's like a 20 bundle Newton method. And within another in this case a couple of hundred iterations, you've got machine precision basically. So it's really quite effective, and you are landing on the active manifold, so you can see the gap between the first and the sixth largest eigenvalue shrinking pretty quickly as you get close to the optimal solution here. So the gap between those eigenvalues is going to close to machine precision. So you're getting a matrix which has a largest eigenvalue of multiplicity 6. Sure enough, you're identifying that very, very accurately. Okay, I'm almost done. There's lots of work to do, which I won't linger on. We'd like to avoid Hessians, obviously, if we could. There are a couple of ways we might want to do that. One way we've been working on is actually using automatic differentiation. XY Han has been working on that. That actually works surprisingly effectively. So actually that's quite promising. If you've got your code, you can use an automatic differentiation routine to sort of pull out gradients and Hessians essentially for free. Or you could think about linear, like first order analogs, where you're just aiming now at linear convergence. So you approximate the Hessian by multiple of the identity. That looks, that's less progressed, but there's promise there. So I think some kind of version of this idea, you might be able to get linear convergence of a first order analog. obviously it would be great to have a convergence proof that's not just for max functions. So it turns out to be quite easy to extend it for at least for weakly convex functions. There's a sort of little tweak to the proof. Again, this is very much a local argument, and so by adding a multiple of the norm squared, you can sort of fool the algorithm into thinking that it's doing something convex, basically. So that's not too hard to do. And more generally, of course, it would be great to do this for partly smooth functions, given the philosophy, and I have no idea how to do that, sadly. So it'd be great to do that. And then, you know, again, the $1 million question. This is I very strongly emphasize, this is a local method. You somehow need to get close. So the question is, how do you globalize it? And you know, that's a problem with any Newton method. The globalization challenge is still sits there, right? So how do we do that? Again, we don't know, but we're thinking about it. And so I'll leave it there. There's the takeaway. This idea of partial smoothness is this sort of basically a very simple differential geometric idea that I think captures the interplay between smooth and non-smooth geometry nicely in concrete variational problems. And it really, not only does it illuminate the analysis, but it suggests algorithm design too. So that's the case that I want to make. And then again, for the recording, there's a bunch of references at the end that you're very welcome to check out. And I'll call it quits there. So thank you very much. And again, thanks for spending your sunny afternoon. And I'd be happy to take questions.
Oh, okay. Thank you. Let's thank Professor Lewis again for the great talk. So the first question is that it is well known that in practice, quasi-Newton works very well for the L1 regularized least square regression. Could you please comment on how your work reveals more insights on that?
Yeah, I would love to say it does, but you know, I'm a big fan of BFGS in non-smooth settings, but to me it is still miraculous. You know, we basically don't understand why it works. Very often when you apply it, it seems to converge linearly, but we just, or at least I don't understand why. So the proofs that we have of convergence of BFGS in non-smooth settings are almost none. We have, you know, there's a little bit, very, very special results when there's an isolated non-smooth point. But, you know, even for functions of two variables, I have no real understanding of why BFGS works in non-smooth settings. And I don't really have a good intuition even. So it's mysterious to me. So I'd love to be able to answer that. So it's a great question.
Okay, thank you. And another question is, how do your theory on the partial smoothness connect to the smoothing technique in classical optimization literature? For example, a Nesterov smoothing.
Right. So those smoothing techniques, they depend on having some kind of knowledge of the structure of the function. So when you do the smoothing, you know, you basically need to know that there's something that you know depends on. You know, the most usual setting is where, you know, you've got, like, for example, minimizing a maximum of some functions or minimizing a largest eigenvalue. You've got some smoothing of that underlying outer function. But to do that, you need to know that structure. That structure has to be visible to you. And so if you're in a black box setting, it's less clear how to do that. Now, there are sort of randomized ways, and actually Nesterov has done work on this. There are randomized ways that you can effectively smooth, but they're very slow. At least in my experience, they're very slow. So you can solve non-smooth optimization in general using a randomization technique, but the complexity analysis is extremely slow, right? So it's a very, very slow technique. The ones where they're really dramatic are ones where you know the structure of the function, and so you've got some kind of smoothing that you can do by controlling some parameter that controls the level of smoothness. And those are highly effective. You know, they're very, very effective ways of solving those problems if you know that structure. But I want to suppose that you don't know that structure. You're completely blind. The only thing you have is an oracle. So.
Okay, thank you. And another question is that suppose there's a local manifold and we know the structure of it. What if we just apply the manifold optimization techniques? For example, the remaining gradient and how to compare with those methods?
Right. I think those are very promising. Again, if you know that structure. So, for example, people have tried to do that in SDP for semi-definite programming, for example. If you know the rank of the optimal solution, once you get close, you know exactly what the structure is, and you could explicitly write down, if you wanted to, you could write down Newton's method, and of course it would converge quadratically, right? But and there are lots of other examples where we have very good algorithms for manifold optimization. Optimization on steeple manifolds, or fixed rank non-symmetric matrices, where we can sort of somehow track that manifold. We can parameterize that manifold exactly and trace it around. But again, that depends on knowing the structure of the problem, where you know what that manifold is, sort of roughly speaking, in closed form. And then you've got a whole wealth of techniques available to you. So again, what I'm trying to do here is suppose that you don't know what that manifold is, but you suspect it's there. You suspect very strongly that that manifold is there, but you don't know how to write down what it is. Right? That's the point here.
Mm-hmm. Thank you. And another question is regarding the implementation of this method. So do you need to do line search for the Newton method, and how to search in the smooth manifold?
Right. So there's two bits to that question. So no, there is no line search in this algorithm. And again, that comes back to this question of global versus local, right? So this is the convergence, the algorithm that we have and the convergence proof that we have are very strongly dependent on taking full Newton steps, right? So you really have to take full Newton steps to, the convergence analysis is kind of delicate. So there is no line search, you just do the full Newton step. So you solve that, solve for that new point exactly. So then the question becomes, well, could you globalize it in the same way that you globalize a traditional Newton method by doing a line search or trust region or something like that? And I don't know. Of course, it'd be great to do that. I think it may not be that easy, again, because the convergence analysis we do is quite delicate. And, the fact that it works is a bit surprising. This sort of k-step quadratic effect that you see is quite surprising. So I don't know a way to do that. Now, as for the question about doing the optimization on manifolds, again, we don't have to track the manifold exactly. We're not doing that. We're carrying along a bundle of points with us that are not on that manifold, will never be on that manifold, but somehow they're capturing that structure of them, they're approximating the structure of the manifold by the fact that you're keeping k of them together as you go along. So we don't need to do exact computations on the manifold.
Okay,
we don't even know what it is. So.
Thank you. Maybe the last question is regarding the possible extension. I was wondering if you have considered, say, extending this work to the setting of minimax optimization, where we want to, it's a bivariate optimization problem, and we want to minimize over variable x and maximize over variable y. Right.
Yeah. So again, it's a good question, and I don't know the answer. What we've done here is very much about optimization. And a good question would be, well, going back to the first framework, does some version of this work for generalized equations? Because what you're describing is something that you write down the saddle point conditions, that becomes a generalized equation. So what's the sort of equivalent of what we're doing in that setting? And I don't know the answer to that. But I think it's interesting. The other thing I would say is that this is only interesting probably for problems where you want to get pretty accurate solutions. So why are we interested in Newton's method? We're interested in Newton's method because Newton's method, when you're done, right? I mean, it's sort of, you run Newton's method and it just basically stops because it's so accurate. But if you're in a very, very large dimensional setting where you're more interested in first order methods because that's all you can do, then these kind of ideas have much more limited effects. You can do acceleration techniques. You can try to do it, and actually in some of my work with Steve Wright, we've tried to do that in composite optimization, at least heuristically. You identify a sparsity pattern, and then having identified the sparsity pattern in lasso, you then can do something higher order, and people do that quite successfully. But in this setting where you don't have the structure, probably you're looking at problems that are difficult in a relatively small number of variables, but what you'd really like quite accurate solutions. That's the idea.
Okay, thank you. So that's basically all the questions I got. Thank you. Thank you again for the great talk and your time with us.
Great, it's a great pleasure, and thank you to everybody out there. It's been really nice, and it's an honor to be here. So thanks a lot.
Thank you.
Yeah, and also thanks everyone for joining. Look forward to seeing you next week.